Hey guys, so that video stopped abruptly. This is going to be a follow-up sample problem for us to look at just the same kind of information and then expand on what we're going to be asked to do in practice problem number 3. Okay? All right, so this is a long equation, and I don't know if I wrote it big enough, but let's just look at this. So this is calcium carbonate is reacting with hydrochloric acid, and then we get calcium chloride, water, and CO2 gas is being given off. So just to review what this means related to the first section is 1 formula unit, 2 molecules, 1 formula unit, 1 molecule, 1 molecule. And then we know that that also relates to moles. 1 mole of calcium carbonate, 2 moles of hydrochloric acid, 1 mole of calcium chloride, 1 mole of water, and 1 mole of carbon dioxide. Then we know that the same thing relates to mass. We add up the mass of calcium carbonate, and since we have 1 mole of it, it's just going to be the molar mass. So that's 100.1 grams of calcium carbonate. The hydrochloric acid, there are 2 moles of it. Each mole is 36.453, so times 2 gets us to here. Then we do the same thing for calcium chloride, calcium, and then the chlorine, or the chloride ion, times 2 for a total mass of 110.9. Water is 18. We have 1 mole of that, and then the carbon dioxide is 44 grams. We have 1 mole of it. So then our last bit of work to do is to show that the reactants equal the products here. So we'll just take our calculator and go 100.1 plus 72.9 equals, that's 173. We're to 1 decimal place, so I'm going to put a 0 there, grams, reactants, yields, and let's do the other side, 110.9 plus 18 plus 44 equals, and that's coming 172.9. And so you can see that in my sig figs here, I don't have exactly the same number. So probably a better number to have for this one instead of this number would have been to go ahead and write this as 111.9, because there was an 8 here actually. So that would get us to our 173.0 grams. And that's actually close enough for the products. So we would not be dishonoring the law of conservation of mass related to that. But so we'll just kind of watch that as we go along. So that's how that relates to all the relationships that I can show from a balanced equation. So now when we talk about mole ratios, we want to take that balanced equation, and then what we're going to do, guys, is talk about just the mole relationship, just the mole relationship of each item. And what we need to remind ourselves is everything in this balanced equation is connected to every other thing. And we want to do it systematically. So this means that 1 mole, and you're going to get tired of these. 1 mole of CaCO3 relates to 2 moles of HCl. They are in relationship to one another. It takes 1 mole of this to react with 2 moles of this. That cannot be any different. So that's a mole relationship. Then I'm going to write a mole relationship. To keep myself from making an error, I'm going to write every one that is valid with this on top. So the next one would be 1 mole of CaCO3 over the first product, 1 mole CaCl2. I haven't gotten my Sharpies yet, y'all. 1 mole of CaCO3 over 1 mole H2O. And then the last one would be 1 mole of CaCO3 over 1 mole of CO2. Now this one has a lot of things to do in it, right? Now, hydrochloric acid, this relationship of hydrochloric acid is related to everything else in this equation. So the next list of possible mole ratios will be 2 moles of hydrochloric acid relates to, and I'm going to go back and grab the other reactant over here, 1 mole CaCO3. And then it's 2 moles of HCl is in relationship to 1 mole of CaCl2. 2 moles HCl is in relationship to 1 mole of H2O. 2 moles of HCl over 1 mole of CO2. If there are 5 items in a reaction, then there will be 4 valid mole relationships, mole ratios for everything in the balanced equation. 1 mole CaCl2 over 1 mole CaCO3. Do you get the idea? 1 mole CaCl2 over 2 moles HCl. 1 mole CaCl2 over 1 mole H2O. 1 mole CaCl2 over 1 mole CO2. Now, what would our last 2 columns be? It would be 1 mole of H2O on top, and then everything in the equation in the numerator. In the denominator. So 1 mole H2O over 1 mole CaCO3. And then on down, 1 mole H2O over 2 moles HCl. Notice that I always put the coefficient that is in the balanced equation. 1 mole H2O, I lost my place. 1 mole CaCl2. I don't put 1 mole over 1 mole of oxygen. Of water, because that doesn't help me. That doesn't change the conversation. And then 1 mole H2O over 1 mole CO2. Then the last column, 1 mole CO2 over 1 mole CaCO3. 1 mole, let's slide this over just a little bit, 1 mole of CO2 over 2 moles HCl. 1 mole CO2 over 1 mole CaCl2. 1 mole CO2 over 1 mole H2O. So we see that a reaction that has 5 components, 1, 2, 3, 4, 5, 5 components, will have 20 valid mole ratios. And it will be in your best interest if you write them systematically, moving from one to the other, going back and starting at the beginning. Everything takes a ride in the numerator, and then everything takes a ride in the denominator with the new driver here. Now, the next section is going to tell us how to use this, right? This will be used to change the conversation when we know one piece of information, but we need to know something else. Okay, so that's how we're going to use this in our next section, and this is the power of stoichiometry, because all of these ratios are related to one another, and any one of them can be used to get us the right information. So we just, in the beginning, we just have to understand how we can write them. When we're actually solving, the good news is when we're actually solving an actual stoichiometry problem, we would not write them all. We would only write the mole ratios that we need. Sounds good, right? Okay. See you soon.